Hi, welcome. In today's class, we're going to look at entropy and how it relates to state changes or changes of phase. So last time, we looked at the second law, and we saw how the second law explained why certain processes occur. Now, another example that we could look at, right, was heat transfer. So we know that heat always moves from hot to cold, right? So if I put ice into water, right, heat is transferred from the warmer water to the cold ice, causing the ice to melt. But what if it happened the other way, right? What if heat moved from cold to hot, right? So what if the heat from the ice moved into the water, causing the water to warm up and the ice to get colder, right? Well, this is forbidden by the second law, which states that the entropy of the universe must increase in a spontaneous process, when in fact that process would cause the entropy to decrease, right? Because we're concentrating the heat within the water, right? We're taking the small amount of heat that's in the ice and putting it with the larger amount of heat that's in the water. We're concentrating the heat in the water. Whereas when the heat is moving out of the water into the ice with the lower heat, right, we're dispersing, right? We're expanding the energy, dispersing that energy, increasing the entropy, right? So the second law can explain why certain processes occur and why others don't. So let's turn our attention to phase changes, though. So back in chapter 7, of course, we talked about enthalpy, right? And just in the last class, we talked about why enthalpy alone isn't our chemical potential, right? But it did bring us some useful information, right? And we will keep using it as we go and try to establish our chemical potential. But one of the other things that we looked at in chapter 7 was how we divide the universe into the system and the surroundings, and that we can look at the flow in and out of the system and the surroundings. So we're going to take that same approach, but with entropy instead of enthalpy. So if we think about the states, right, when we looked at the melting and the condensation, the evaporation of water, right, we saw that those processes increase the entropy, right? So when you go from a solid to a liquid, the entropy increases. When you go from a liquid to a gas, the entropy increases. So what that allows us to understand is that as we move to these different phases, we can rank them in terms of entropy. So when we go from, say, a solid to a gas, right? If we were to melt and then evaporate, we go from a very low entropy system where there's very little freedom of motion to a much higher entropy system in a gas where there's all kinds of movement, rotational, translational, along with some sort of vibrational movement. So during this process, this solid to gas transitions, we get increasing amounts of entropy. So we can therefore rank the entropy of the phases that a gas will always be higher in entropy than a liquid, and a liquid will always be higher entropy than the solid form. So solids the lowest entropy, gases are the highest entropy. And we can look at this somewhat graphically. If we look at, so the solid is warming up, it's transitioning, then it goes through the melting, and we see a large increase in entropy here, and then it's heating up. We get more entropy increase because the water is moving faster. It's getting warmer, that's going to increase in entropy. But then during the phase change, during the evaporation, we see this large increase in entropy again to get to the highest entropy form, or the gas. Okay, so we just established that there is a different amount of entropy in different phases. So gases have highest entropy, most randomization, most dispersal of energy. Solids have the least, liquids being in the middle. So if we look at these phase changes, right, again, we saw that melting and evaporation had an increase in entropy, but they had a decrease in enthalpy, right? Because we can't forget that there's heat flow going on, right? We just explained how these entropic or how these endothermic systems could be spontaneous, and that is because we have a positive or an increase in the entropy. So what that means is we can define this change in entropy based on the heat change, based on the heat flow. So what we say is that the change in entropy of a system is the heat at a constant temperature, right? So we can define the change in entropy as the heat at a constant temperature. So delta S would equal the amount of heat divided by whatever that temperature might be. Now, this equation, while useful, is a very specific equation, and it only applies to a, quote, reversible process. Now, to strictly speaking, a reversible process is one that reverses direction upon an infinitesimal change in some property. So, in the example we were looking at, that infinitesimal property is the heat flow, which we observe as a change in temperature, right? So at a specific temperature, like the boiling point or the melting point of a system. So for example, if we're at 0 degrees Celsius, right, the normal freezing / melting point of water, an infinitesimal removal of heat, right, will lower the temperature, and it will reverse the melting and cause freezing. So if we instead add heat back and we raise the temperature, we'll switch that freezing back to melting once the temperature rises above 0 degrees. Now, this reversibility is under ideal conditions, right? And is not observed in most real-world conditions. So, for example, an ice cube sitting on your table at 25 degrees or in a glass of water, right, is not reversible, right? We're not at that normal melting or normal boiling point, right? And so removing a small amount of heat doesn't reverse the process. So that ice cube is going to melt if we change the temperature to 24 degrees, just like it would at 25 degrees, right? It's not irreversible in this sense of the definition that we talk about, right? So it's what we would call an irreversible process. So we just showed how endothermic processes like evaporation and melting can be spontaneous because they have an increase in entropy. So now let's kind of turn the tables here and look at some processes that have a decrease in entropy, namely condensation and freezing, right? These see a decrease in entropy. We're going from a less ordered state to a more ordered state. Now, how is that possible? But yet, these are spontaneous. So we've defined the second law to say that the increase in entropy of the universe is necessary to have a spontaneous process. But if the process itself has a decrease in entropy, how does that process still spontaneous? Well, the key here is to understand the significance of the universe, right? So, as we alluded to before and back in chapter 7, right, when we talk about thermodynamics, we divide the universe into the system and the surroundings. So, what we can say is that if indeed the entropy of the system goes down, right, as we see with something like freezing or condensation, then it makes sense that the entropy of the surroundings would have to increase by more than that in order to make the entropy of the universe positive. And so that's exactly what has to happen, right? So if we require this to be positive, but yet this is negative, then this has to be positive more than the delta S of system is negative, right? So we need it to be a bigger value. And so if the process is spontaneous, but the entropy of the system is negative, unfavorable, then we must have a large enough increase in the entropy of the surroundings. Now, how do we get that entropy increase in the surroundings? Well, it must come, or it comes from, the increase in temperature of the surroundings. So the entropy increase comes from heat released by the system to increase the temperature of the surroundings and therefore increase the entropy of the surroundings, right? As the surroundings gets warmer, the molecules will move faster, right? We're getting that energy dispersal, right? We're going to increase the entropy of the surroundings. So bottom line is that in order for systems like this to be spontaneous, they must be exothermic. So if a system has a decrease in entropy, then it must also be exothermic so that we get an increase in entropy of the surroundings and therefore an entropy increase of the universe. So let's look at some graphs just to kind of drive this home. So for example, graphically, if I have a decrease in the entropy of the system, then my reaction must be exothermic enough to cause a bigger increase in entropy of the surroundings so that my overall entropy change of the universe is positive. So if we look, for example, with water freezing, right? We know that this isn't spontaneous at all temperatures. Water doesn't freeze at any temperature. It only freezes once you get below 0 degrees, right? So what we can see is that at lower temperatures, right, this entropy of the surroundings becomes big enough to overcome the entropy of the system, or the negative entropy change of the system. But at higher temperatures, so in other words, temperatures above 0, and for freezing anyway, this increase is not big enough to overcome the entropy of the system, and so we end up with a negative increase in a negative change in the entropy of the universe, and therefore a non-spontaneous process. So these changes are temperature dependent, right? They may occur at some temperatures but not others. And so the temperature of the surroundings is critical here, right? The other thing that we can take home is as the surroundings become higher and higher in temperature, the same amount of heat being added to them, right? It's the same process going on, doesn't have as big of an effect, right? So, in other words, if the surroundings are already more energetic, then adding a small amount of energy doesn't make such a significant change. But at lower temperatures, when the surroundings have a low amount of energy, adding only even a smaller amount of energy cause a significant increase. So there's going to be temperature dependency of this effect as well. Okay, so what we just saw was that the entropy change is temperature dependent, right? That this reaction is not going to be spontaneous at all temperatures. So we just saw for freezing, and right, we can remember the relationship that we saw earlier. And now this was for a very specific condition, right, at the normal freezing or boiling point. But generally we can say, right, that the change in entropy is going to be dependent on temperature, right? We can see that temperature dependency here. So in this case, at higher temperatures, this entropy change is not enough to cause the overall process to be spontaneous, right? It's not going to increase the entropy change in the surroundings is not going to be enough at this higher temperature to flip to make the process spontaneous, right? So there's a temperature dependency increase in that reactions are not going to be spontaneous at all temperatures, right? That's sort of a bigger take-home message here. So what we can look at now is a summary of kind of what we've done so far. So we've seen that there are two factors that are going to play a role in whether a reaction is spontaneous, right? The enthalpy change and the entropy change, right? So whether something is endothermic or exothermic plays a role, but also whether it has an increase and decrease in entropy can also play a role. So just remember our definitions, right? The enthalpy change, right, is the sum of the internal energy and PV work of the reactants going to the products, right? So remember the other way that we thought about this was Q at constant temperature equaled the delta H, right? So we looked at the heat flow at constant, not constant temperature, sorry, constant pressure equaled our enthalpy. Now, the entropy, as we've just discovered, right, is the difference in randomness or energy dispersal of the reactants compared to the products. Okay, and whether that gets higher or lower determines our delta S. Now, we also looked at specific types of enthalpies, right? We said that if a system is exothermic, meaning it adds heat to the surroundings, then it will also increase the entropy of the surroundings. So exothermic increases the S of the surroundings. But an endothermic process does the opposite, right? It takes heat away from the surroundings, which decreases the entropy of the surroundings. And the amount of this change, right, the amount of this delta S going up or down depends on the magnitude of the enthalpy change, right? So the more heat that is released into the surroundings is going to cause a bigger change in entropy. And also we established that it also depends on what the starting temperature is of our surroundings, right? If the starting temperature is also already at a higher temperature, then releasing the same amount of heat is going to be less significant, right? So lower temperatures are going to be impacted. Surroundings at lower temperatures are going to be more impacted by this increase in heat, or they're going to have larger changes in the entropy. So bigger impact when the surroundings are at a lower temperature than at a higher temperature. Now, we see this, we saw this example before, but just to reiterate, we see this example, we know that water freezes spontaneously below zero because the heat released on freezing is enough to flip the entropy, right? To increase the entropy of the surroundings enough to make delta S of the universe positive. But once you get to higher temperatures, the amount of heat that is put into it, to the surroundings, does not increase the entropy enough to make delta S universe positive, right? And so the entropy change in the surroundings is proportional to the magnitude of its enthalpy change. Right? So remember some of these key relationships, that the enthalpy change of the surrounding and the system are the same but opposites. Okay. So we're looking at the enthalpy change of the surroundings. So and also the entropy change of the surroundings is inversely proportional to its temperature. Okay. So lower T is going to get a bigger bump in S with the same amount of heat. So it's inversely proportional to temperature. So we can put all that together to come up with an equation to look at the delta S of our surroundings. So how much does the entropy of the surroundings increase under given circumstances is directly proportional to the entropy change of the surroundings, or excuse me, the enthalpy change of the surroundings, or so we can measure it in terms of the system, it's directly related to the negative entropy change of the enthalpy change of the system. It's inversely dependent on temperature, so the delta S of the surroundings equals the negative delta H of the system divided by the temperature. And of course, this is at constant pressure and constant temperature, right? We're at a given temperature and our pressure is constant, right? That's why we can use the enthalpy numbers here. So that brings today's class to a close. Next time, we'll be looking at another thermodynamic quantity known as free energy and tying enthalpy and entropy into this concept.